Alright, hell yeah. So we're going to do some linear algebra. We're going to do the Gram-Schmidt process. And we're going to do this equation right here. So the first one is just straightforward. The second one, kind of tricky. And then the third one, hell yeah. Okay, and so the first one's kind of going to look like a triangle like this. And booyah, I started this video and almost struck out, but I found out something new. Because what we're going to start out with, if we're going to do the three vectors, and what we're trying to do is we have three vectors and they're just all wonky, you know what I mean? But they are linearly independent. Like none of these vectors are in the same direction, you know what I mean? That's one way to look at it. Hell yeah. And in 2D space, we talked about how if I have two vectors, you know what I mean? This is how we walk across the earth. I'm going to go this way and that way. And if these are my two vectors, I can go anywhere. But, you know, let's say you walked, you know what I mean? Let's say you walked like this, you know, like that. You, like, took a step this way and then took a step that way. You could still go anywhere on earth because you can walk back this way and maybe you can do this way. Those are linearly independent. It's just, it would be nice if we could do this. It could be like, hey, if I want to go over there, it's like, hell yeah. Okay, so keep in mind that these are three. So this is going to be my V1. This is going to be my V2, and this is going to be my V3. They're all wonky angles. The first thing we do is we set our first one equal. Our first one is going to be our perpendicular. And so that's kind of interesting, you know. And so you might as well call this maybe the x-axis. Now, what happens is just like, well, couldn't I draw a perpendicular line here? And that's where I got hung up. And like, couldn't I draw a perpendicular line here? Sure. But if you have two vectors, you know, like let's say it's an array in space, you can only put a flat sheet of paper. You know, if this is a note card, and here's my two vectors. I'm going to be fumbling. You know what I mean? There you go. If those are where the vectors are facing, that's going to be plane. You know, that's going to be plane. But if you say that these are your two vectors, this has to be planar. And so, booyah. So if I do draw a perpendicular line, so if these are the two vectors, the note card is going to be placed right on there. It just happens that I drew the first two vectors, so they are actually taking up this xy space. So this is y, this is the x direction. Hell yeah. But this third one is not in the z-axis. It's wonky. And so that's going to be part of our deal, is we're going to have to find a perpendicular. Hell yeah. And can we do this? We can probably do it in 10 minutes. So for the first one, you're going to say, hey, this is V2. Well, what are we going to do? Well, we just defined that this was perpendicular. And then so we're going to define this as a vector. That's going to be P2. Then we're going to say, well, I know P1. And so, so let's box this in. We know that vectors, you know, follow the visual properties of triangles. And if I know this is P1 out to this point, I can just say, hey, this vector right here is just some sort of scalar of V1, and I'm going to call it K1. And now we're ready to bust it out, because I can say V2 is just K1 P1 plus P2. And this is the first aha moment where you're just like, what are we trying to find? We're trying to find this. Well, rearrange it for that. So this is P2 is V2, and then subtract K1 P1. Hell yeah. So now we're going to jump ahead, because when we do find P3, so let's say we found this, you know what I mean? We actually know, we know everything. Okay, now we're going to jump to, now I have a third wonky vector, and what I'm trying to find is, and I know my first two. My first perpendicular is there. That's P1. My second perpendicular is here. And these are transmissible. It doesn't matter if I put P2 there or if I put P2 there. Those are the same. It doesn't matter if I put P2 right here, which we do in a second. Okay, hell, I just know them after solving for that first go. And then for the second go, I have another wonky vector. That's V3. And then so I'm going to do that same process, because I'm finding perpendicular vectors. There's the first one, there's the second one. And like we said, I'm trying to get to over here by going this way and then that way. So let's go to V3 using at least what we know. So I'm going to go to V3 going along our first perpendicular. Hell yeah, I'm going to go that far. And then I'm going to go along, our second perpendicular. And then I drew this, so I actually have to go farther than P2. P2 is just right there. I have to go all the way up to there. So there's going to be our little difference. And then I need to go in a perpendicular direction. So here is the plane, and perpendicular, if I'm saying this plane is the board, perpendicular to that is out of the board. And so in XY space, we just draw that, have to draw it at some sort of angle so you can kind of see the vantage points. But hell yeah, so this is that direction. And so now I can say this is P3. And so I could say that's P3, but I also drew it in two different ways. I could go this way, I could go this way and then say this is P3, and then go up in P2. Hell yeah. And it's really good for this proof to be like, hey, draw your first P1 way out here, because we had to use a K1 P1 for our first go. So for our second go, we're going to get rid of that. For our second go, we're only going to go this far in P1. So this is a new K1 P1. And then I'm going to go, this far in P2. So this is going to be K2 P2. I have it drawn over here. But you can easily see the difference between what P2 is. And K2 is going to be a scalar multiple of P2. Hell yeah, we got 3 minutes. Alright, booyah. So then we have P3. So we're going to say V3, to actually get there, is a stair step, is going to be K1 P1 plus K2 P2 plus P3. And at least right here, you can be like, aha, there's P3. So we're going to write P3 is V3 minus K1 P1 minus K2 P2. So we have our equation, we just don't know what K1 or K2 is. But we do use the dot product. And I only have 3 minutes, so we're just going to go for it. We're going to take the dot product of V3, and we're going to dot it with this P1. So we're going to do the dot product, V3, P1. We write it like this. You might be more familiar with it like that. But what happens is we're going to say V3 is actually K1 P1 plus K2 P2 plus plus P3. And then we're going to dot it with P1. Hell yeah. And then this could be also, and we can FOIL this through. So if you're more familiar with it like this, K1 P1 dotted with P1, K2 P2 dotted with P1. And then P3 dotted with P1. Well, what happens is we already said P1's perpendicular, P2's perpendicular, and this V3, when we dot it with, and we're saying that V3 is K1 P1, K2 P2, and this new perpendicular. That if I'm dotting it with P1, only these two will actually generate a value. These will generate 0. Two vectors that are perpendicular will be 0. So then we have this inner product, V3 P1, is equal to K1, and then we have the dot product of two vectors, which is just their magnitudes squared, because you get 100% of them, so it's just the magnitude squared, and then we solve for K1. K1 is V3 P1 divided by the inner product. Alright, hell yeah. And that's, we got 48 seconds. And then we would do the same thing. We would dot V3 into V2. And so you do the inner product of V3 into P2. And so this is V3. And then if I throw a 2 here, only these two are going to generate. And we got K2 and then the inner product P2. Hell yeah. And we got 20 seconds. So I didn't do it in 10. Maybe we'll try again. But then you're going to throw those values into this equation for K1 and K2. And that's going to be your answer. And then so in 9 seconds, here it is. This value is K1, this is K2, and again, hell yeah.